Hello students. In this video we'll show you some applications where we need to use quadratic relationships in order to answer some questions. Okay, let's start with this question. So I'll just read out the first part of it. Kayla, a keen golfer, hits a golf ball along a fairway. The height of the golf ball h in meters at any time t in seconds during its flight is given by the equation h equals negative 5t squared plus 20t. So step A, or part A, complete the table of values for h and t, which is on the next page, and B, plot the graph of the equation. And then we'll come back and look at the actual questions based on that shortly. So let's go ahead and start this. So here we have the equation, h equals negative 5t squared plus 20t. This, by the way, is a really common application of quadratic relationships. Anytime you have an object that's moving only under the influence of gravity, such as a golf ball, it turns out that the relationship is quadratic. So this is one of the places where we use quadratics all the time. Okay, I'm just going to do the first couple of points just for practice. We don't need to do the whole thing. I think you know how to do it by now. So let's start by putting in 0. In fact, 0 I can do myself, so I'm not going to even bother using the calculator for that, because 0 squared is 0, negative 5 times 0 is 0, 20 times 0 is 0. So when t is 0, h is 0. So that one I don't need my calculator. We'll do the second one with the calculator, however. So negative 5 times, now because this is a positive number, I don't have to use brackets, though I can if I want to. So negative 5 squared plus 20 times 0.5. Okay, quick check. I've got negative 5 times 0.5 squared plus 20 times 0.5. That looks pretty good. And I get 8.75. Okay, and I could go ahead and continue to substitute the rest of those values into the equation to complete the table, but in the interest of time, I'm not going to do that. I could then go ahead and plot the points, but that's already been done for us. So when you finish that part of the equation, parts A and B, that's what you should come up with. Okay, let's go ahead and now answer some questions based on that. So here's the questions just over here. So how high does the ball get above the ground? Well, we can looking at our graph here, height is on the vertical axis. So after 2 seconds, it reaches a height of 20 meters. So the answer to the first question, 20 meters. How long does it take to reach this maximum height? Well, that's just the x-coordinate of the maximum. So it's 2 seconds, since the units here are in seconds. When does the ball first reach a height of 12 meters? Well, we come over to the height of 12 meters, draw the horizontal line to the graph, and then straight down, and we read off the value on the x-axis. So in this case, halfway between 0.5 of a second and 1 second. So that's going to be 0.5 seconds. And how long does it take before the ball hits the ground? Well, that's when the height goes back to 0. So that's going to be 4 seconds. And for how long was the ball at least 8 meters above the ground? Well, once again, we go to a height of 8. We put in a line, horizontal line at 8. And now we've got to estimate. It first reached a height of 8 somewhere around about 0.4 seconds. It's approximate. And the other time it reached it on its way down was about 3.6 seconds. And the question is, how long was it above that height or more? So we have to just subtract. So 3.6 takes 0.4, and the answer is approximately 3.2 seconds. Again, we could actually use the equation and get a more exact answer. Okay, let's look at a second application. Once again, because we've already been drawing a fair few graphs in previous videos, I haven't bothered to go through the process for making the table and drawing the graph. If you're not too sure how to do that, go back and look at some previous videos. But for now, there's the graph of the equation just there. So the volume of liquid in a container can be found using the equation V equals 3t squared plus 4t. V is measured in cubic centimeters because it's the volume. T is the number of seconds after pouring commences. So part A has already been done for you. Let's have a look at questions B through F. So find the amount of liquid in the container at the start. Well, at the start means when T is 0, and that means the volume is also 0. So the container is empty when we begin. Oops, that should have been down there. Find the amount of liquid in the container after 4 minutes. Well, from 4 minutes, I'm going to go get a nice tool for this. My vertical line tool. I go up to the graph, and then I go across. And it looks like it's going to be something like about 63, approximately 63 cubic centimeters. Whoops, let me go get my pen tool. So again, we can only estimate it from the graph. If we need it more accurate than that, we have to go and use the equation. The container can, excuse me, the container can only hold 132 cubic centimeters. How long in seconds does it take to fill the container? So once again, I'll get my horizontal line. I go up to 132, so a bit over halfway between those. Oh, there we go. We're lucky. We've got the exact value just there. Let's say we didn't have it. Then I would do that, and I can come down to here and say the answer is 6 seconds. So in this case, it turns out that was one of the values that we used to plot the point, but that doesn't always happen. So the general way to do it is come across from the vertical axis to the graph, straight down, and then read off the value. How much liquid is added in the first 2 seconds? Well, we can, once again, I'll just read it off from here. There's 2 seconds. We go up to the point. It turns out it's one of the values that we plotted, but if it hadn't been, you come across, and that's going to be 20 cubic centimeters. And what are the feasible values for time and for volume? Well, because we can only hold 132 cubic centimeters, for time, it's really only sensible to plot this between 0 and 6 seconds. Because after 6 seconds, it's just going to start spilling over, so you're not going to add any more liquid to the container. And obviously, in this situation, you can't talk about time being negative. So we have to start when time is equal to 0. And for volume, well, when we start, it's empty. So 0 cubic centimeters, and it can only hold 132 cubic centimeters. So therefore, it doesn't make any sense to talk about a volume greater than 132 cubic centimeters. So when you're doing practical applications, you do have to restrict what's on your x-axis to something sensible, in this case 0 to 6 seconds, and restrict what's on your y-axis, the variable on your y-axis. In this case, we can't have a negative volume, and 132 cubic centimeters is its maximum volume. Okay, we'll leave it at that. That's a quick introduction, or fairly quick introduction to quadratic relationships.